Hello everyone, today we're going to go over Diels-Alder and paracyclic reactions. So what's on the agenda for today is first off the mechanism and transition states which exist, of course in the flash, and a more stable product is formed. Conformation of dienes, or where how they are either an a cis conformation or a trans conformation. And this is also going back to Le Chatelier's principle, because as you know, trans dienes are much more abundant than cis, and so that's really kind of the holdup in terms of making product in paracyclic or Diels-Alder reactions. Okay, as well as bulk and what will prohibit anything to going into a cis conformation. Number 3, constituent effects and energetic barriers of product or ring formation. Okay, so whether something is electron withdrawing or electron donating that's attached to the diene or dienophile, as well as whether or not that'll perturb or completely inhibit that correct conformation. Number 4, stereochemistry of reactants and products. For the bicyclic compound formation. So that's also, referring to exo and endo products, which we'll get into later. Number 5, regiochemistry from electron withdrawing and electron donating effects. So really, it's almost a matter of magnetism, going from net positive to net negative, or partial positive to partial negative, and matching up. Retro Diels-Alder, so basically working in reverse. Certain things can go backwards in terms of, how stable they are as, we'll say, monomers as opposed to a dimer. Then oxidizing species, so we're just going to go briefly over some of those, where you can form a cis diol or other species, as well as breaking up double bonds. And then lastly, we're going to go over thermally or photochemically allowed and forbidden dimerization or some kind of sigmatropic rearrangement, if you will. Okay, so let's first get started with a very simple kind of example here. So the first being, what exactly is a Diels-Alder reaction? Well, first, there involves a diene. So again, right now this is in the cis conformation. Okay, so this is cis right here. Then remember that this is going to be an equilibrium. It's going to be far greater, thermodynamically more stable trans conformation. Conformation, not configuration. So there's a difference, all right? So that means there's a rotation between these two carbons here, about that single bond. All right. Now, then you have the dienophile, which is on the right here. So notice how I also put the total count of pi electrons here. So there are 2 pi electrons for ethene, and then 4 for 1,3-butadiene. Okay, so when everything connects, and basically these pi bonds act as almost lone pairs, and there's sort of a cascade effect where you're going to form some kind of intermediate. Okay. So we can pretend that everything that I have here is this hexagon is sort of like a sigma construct, and then there's this sort of transition state within here. Okay, so when you see this double dagger sign, that means it's going to be in a transition state. If there are 6 pi electrons, right? So 4 plus 2, in other words, or 4n plus 2 as you think of with Huckel's rule. So this is a stable transition state complex. That's not to suggest that you can get out of a bottle. This is just something that is actually stable given these conditions and where it actually leads to, and that actual product is going to be eventually forming So in other words, this double bond has been pushed up. It's pushing this out to form 2 sigma bonds. So the 2 sigma bonds that are established here are between the dienophile and the diene, basically working in concert. Okay, so in other words, all together. All right, so now you see here that you have what cyclohexene is your product. So this is going to be more stable than these 2 forms alone. Okay, so while there is some some conjugation going on right over here, again, you have to get this up into higher energy in order for it to go from trans on the left here to cis. Okay, so again, a sum of 6 pi electrons, all about the same pi electron plane. Okay. Okay, so let's say we take 2 equivalents of ethylene just for argument's sake. We try to combine them together. We're going to have 4 pi electrons, and you can think of that if you were sort of imagining a planar structure with 4 pi electrons circling about it, you would think of that as being anti-aromatic, right? So what you would see here is a square, right? But this is not going to, this is what's going to be referred to as thermally forbidden, okay? So if you have 2 plus 2, does not equal 5, it equals 4, right? 4 pi electrons, right? And this is all, again, within the transition state. So in other words, the overlap that you're going to see here isn't going to be feasible. Okay, so in other words, it's just going to go back to being 2 equivalents of ethene. All right, so we'll get into some molecular orbital theory pertaining to that. You can see some actually really good examples in your text. It's really a great job how they nail it in terms of explaining why the molecular orbital theory just makes so much sense with this, particularly with frontier orbitals and what have you. Okay, so let's think about the following diene and dienophile. Now notice that you have a trans diene here, and you have 4 pi electrons once again. Really the problem here is that you're not going to have a whole lot of freedom of rotation there, seeing as you have all these other carbons that are bound to one another about this bicyclic ring. So in other words, this isn't going to be able to basically twist and get to the point where it's in a cis conformation. And therefore, you're really not going to get any type of transition state intermediate because things can't overlap effectively. Okay. So this is something to consider, especially if you have some substituents, let's say, about a cis diene. If they're really bulky, come on, focus. Okay. So think about if you had some bulky substituents that were, let's say, truly cis configured with respect to this alkene, right, or this alkene above. If they were basically bumping into one another over here, it's going to really slow things down or make it almost impossible for any paracyclic reaction to occur. Now, so far, we're okay with the steric effects. So we just saw how fixed dienes react or don't, right? So if there are physical barriers of rotation from electron repulsion, in other words, if those things are bumping uglies, the reaction rate will decrease, right? So it's going to slow things down. But before we jump into kinetics and see how fast or slow things go, let's examine a couple of problems. So why don't you guys take a look at 24.29, problems A, C, and D on page 1237 in your text and see what you come up with, and then we'll put that in. So pause.